I want to thank everyone for coming. I'm Wes. I'm the Director of Engineering at Cortico. We're a nonprofit production arm embedded within the Lab for Social Machines at the MIT Media Lab, which is kind of like a stacking doll of different orgs, but I'd be happy to talk more about this later if people are interested. So today I'll be talking about a topic detection system that we built to find local events of interest in Twitter and other sources of data. And a note on the title of the talk, this isn't a theoretical thing that we came up with and wrote a bunch of papers to prove that it's optimal. This is actually a production system that we built that's fast and it gives us reasonable and interpretable results. But that said, I'm going to go with the Feynman admonishment that I should bend over backwards to show you how the system doesn't work well, as well as how it does work. So. Okay, so just to get some context, so Cortico is a nonprofit inside of the Media Lab, and the goal of the group is to foster a healthy public sphere, which is admittedly nice and grand sounding, kind of vague on the details of what that actually means. So we take inspiration from Habermas's definition of the public sphere, where there are three components. There are people, the media, and institutions. People represent individual voices, right, like you and me. Institutions are typically groups of people, but it could be celebrities. But it's a group of people who have some sort of coercive power on people who are in the out group. So you think, for instance, government or private corporations, but it could also be smaller entities like your neighborhood association or your school PTA. And then the media is the place by which we transmit ideas that we can debate so that the institutions can be checked. But also so that the institutions can understand the needs of the people. So these ideas or things which we can debate is really the core motivation for the technology that we're building that I'll be describing today. And we call these things which we can debate events because they tend to be temporal in nature, like someone gets elected or something of really local interest happens, like bears are spotted roaming in the neighborhood. And we call these, we call our system an event detection system so that we can distinguish between it and more coarse-grained persistent topics. So an event might be a particular thing like some erratic president tweets, but a topic might be something persistent like politics. Though we ingest multiple types of data, the two that we actually surface at the moment to our users are talk radio and Twitter. We process a couple million tweets per day, and thousands of hours of talk radio per day runs through our custom speech-to-text system. And our talk radio corpus is, we believe, the largest of its kind that has ever existed. And so this talk really focuses on event detection in Twitter, and for reasons that I'll talk about later, why it doesn't work so well with talk radio. So I just want to give you a quick glimpse of one of our products so you get an idea of what it is that we're after. So this thing is called Earshot. It's a tool that we face towards journalists so they can better understand what's happening in their communities. We grab talk radio and data and tweets, and then we throw it into an index that's searchable in various ways. From this interface, this one screen, journalists can pick out local stories of interest. They've written stories on this, and in one case they even broke a story about a campaign finance violation in Rhode Island using the data that, as far as we know, is only available to us. So on this screen you can see Twitter clustering, and this is off of our Discover page. And each of these events is automatically generated, and we show representative words for some cluster. Oh, I'm sorry, I just noticed that the resolution on this thing looks terrible, so I don't know if you'll be able to read anything. So we have words that represent each cluster, as well as what we call a representative tweet. All right, I hope the legibility is not an issue. All right. So what are we working with? So Cortico has developed a method for Geo Ranging tweets. So this is roughly saying, okay, based off a set of local influencers, institutions like schools, museums, municipal services, politicians, local celebrities, we can infer if a particular account often interacts with influencers or not. And if so, then we say that they're geo-ranged to that area. I won't get into exactly how this works, but the end result is that we have a collection of tweet streams, one per city in the US that we service. So roughly roughly a dozen at the moment. We stream these tweets, which end up in S3, and then on a per-hour basis, we load up the trailing 24 hours of tweets and run our system on that. And the contents of each one of these tweet files looks like this. If you've ever worked with Twitter data before, you've probably seen something like this. It's a big mess of JSON. So a tweet object contains a lot of data from the tweet body to the metadata, such as the name of the person tweeting, information about the account of the person, their follower count, their following count. And there are a variety of ways that you might be able to use this data. But like you could, for instance, overweight people with lots of followers, so what they say becomes more important. But for our system, we don't do anything like that. We basically just throw out everything except for just the content of the tweet. OK, so just to restate what I said, we only look at the tweet body, and so we extract just the content of the tweet. We do note if the thing was an original post or a retweet. OK, so where do we go from here? We'd like to bring these tweets together into related clusters, and there are a variety of techniques for doing this, which I'll give a very, very fast tour through. Then I'll talk about how we don't use any of these things at all. So Kmeans. Kmeans is perhaps the most well-known clustering technique. We start with an assumption that we have our tweets located in some space where we can calculate a distance between them. And then that we'll be finding K clusters. Then we'll go through a process of figuring out what those clusters are and refining them over and over again. So the first thing we do is we pick K random tweets as our first K clusters. All right? And then we look at all of the other tweets, and we assign them to the clusters that they're closest to. So now each cluster gets just a little bit bigger, right? And we can take that cluster, and we can recompute its center, and then repeat the process. Take all of the tweets again, reassign them to the new locations that they might be closest to, which change the shapes of the clusters again. And we just keep doing this over and over again until the clusters converge, and we aren't reassigning these tweets anymore. And once that's happened, we're done. LDA. LDA is maybe the workhorse of these kinds of topic modeling techniques. LDA is interesting. It makes a few assumptions. So the first assumption that it makes is that a topic is a distribution of words. So a pets topic, for instance, might be well represented by the words dog and cat, but not at all by the word asparagus. The second is that a document is a mix of topics. So a document might mostly be about pets, but it might also be about veggies. And then the combination of these two assumptions gives you a way to model a collection of tweets. So in other words, you can use some definition of topics as words and generate a new set of tweets that statistically look like real-world tweets. They'd actually look like nonsense. LDA throws out a lot of information about the structure of the language and just looks at collections of words as if they were just statistics. But that's fine because it fulfills all the properties that it needs for further clustering stuff later. OK, so that's how you get tweets from topics. But actually, we like to go the other way around and get topics from tweets. Okay, so how do we do that? So we do something that's kind of like Kmeans. So we start with K empty topics, and we go through every word in every tweet, and we randomly assign it to one of these topics. So now we have a set of really terrible topic models, and we'd like to refine it. So then we go through each word of every tweet again, and we say, OK, which one of these topics most likely produced this word? And then we update that word's assignment to its new topic. So the topics get just a little bit better, right? And we keep doing that again and again and again until it converges in the same way as Kmeans. So there's a really neat thing that comes out of LDA, actually, which is that you get these word distributions that represent the models. And these tend to be a much easier way for us to interpret the output. In the case of Kmeans, we just get clusters of tweets, and then you would have to read through them and try to figure out in some way what that cluster is about. With LDA, you get the important words that define each topic. So this is a thing that we'd like to have if possible. Non-negative matrix factorization. So this is the cool kid on the block right now. I actually haven't personally met anybody who's used this thing, but I read stuff about how it's so great. So I can't really comment on the quality of the output or what it's like actually implementing this thing, but it's it is something that researchers are excited about. I think I'm not totally sure, but as far as I know, I think it's in pretty major use on Netflix and Spotify. So the basic intuition is this. Okay, suppose we set up a matrix where on one dimension we have all of the tweets, and on the other dimension we have all of the words. So we can fill in the matrix with values that we know. So like if, for this example, so tweet 1, let's say, contains word number 2, so we mark a 1 there, and then tweet 2 contains word number 1 and word number 3, so we mark 1s there, and then tweet 3 contains words 3 and 4, so we put marks there. Just imagine in an actual corpus, this thing is much, much larger. So you can take this matrix and you can factor it into two smaller matrices with some intermediate width k. You'll see k is this kind of recurring thing that's happening with all of these algorithms. But in this example here, I've just made this simple and I picked a k of 2. Again, like in the real world, you would have much larger matrices and much larger values. What NMF does then is it generates these two factors of the larger matrix, right, such that the k's represent a kind of hidden latent structure. So in the case of the top matrix, we have tweets that would be assigned to topics k1 and k2. And then in the case of the bottom matrix, we'd have words assigned to the topics k1 and k2, right? So we get a description of the topic 2, which is nice. And the way that NMF does this is using a well-known mathematical process called magic. All right. Okay, so now we have a few potential techniques under our belt. How do we actually set up our data? I'm only going to give an example for the Kmeans case. And for that, we just need to be able to say how far away two tweets are from each other. So there are a few methods for doing this, but most require being able to place the document into some kind of a vector space. That's beyond the scope of this talk, so instead I'll just show how we can use something called the Jacquard index to do this. Okay, so this is the Jacquard index. So suppose we have two documents here, and our first document is me before strange loop. I'm not a real programmer unless I know Haskell. This is actually a tweet from last year. Our second document is me after strange loop. I'm not a real programmer unless I knit. I think someone had given a talk about programming looms. This to me just kind of epitomizes what strange loop is about. So the Jacquard index is the size of the union of all the terms in these two documents. So if we keep it simple and we just say, okay, so the terms for the documents are just white space broken up tokens and then sentences, our first document becomes strange loop, Haskell, I'm me, a before, no, not programmer, real, unless. And our second document is strange loop, I'm me, a after, knit, not programmer, real, unless. And then the intersection of the two is just which words overlap. Strange loop, I'm me, a not programmer, real, unless. And the size of that thing is 9. So that's the value of the Jacquard index, and that's a pretty high index because it's pretty close to the length of the actual sentences. So in contrast, some document, a strange loop is a cyclic structure that goes through several levels in a hierarchical system, has a Jacquard index of just 2 with the other 2 sentences. The words a and strange loop are the overlapping words. So if we're lucky, the Jacquard index will give us a rough quantitative notion of how similar 2 documents are, and that gives us enough information to plug into Kmeans so that it can do its thing. So with Kmeans, we still have the problem of being able to recompute centroids, which the Jacquard index doesn't make that very easy. But the way that we can do that is for every cluster that we have, when we want to recompute a centroid, we can pick a representative document in that cluster and then pick the entire set such that they're all as dissimilar as possible. So there's a problem, though, which is that things get a bit dicier with very short documents. So in this example, tweet A, they're good dogs, Brent. And tweet B, they're bad cats, Sally. So there's clearly some relationship between the tweets, but the Jacquard index or any distance metric that looks at just the words in these 2 documents doesn't fully capture it. So the only overlapping word here is there. but the structure of the sentence is similar, right? And what's more, the type of the words, good and bad, are the same. The type of the words dog and cats is the same. The type of Brent and Sally is the same as well. So we have a case where we'd like to be able to infer the similarity in these documents with a pretty low amount of information. And in fact, if you consider a really degenerate case, you want to be able to determine that these two tweets might actually be talking about the same thing, but there's zero information in the documents themselves that might actually tell you this. So you might be thinking, yeah, that sucks for Kmeans, but what about one of the other methods? They all suffer from similar issues like this. So with LDA in particular, and I'm picking on that one because it's the popular one, right? It models these documents as mixtures of topics, but there isn't, with just one word in the document, there isn't much that you can really say about the mixture of anything. Okay, so how do we, as humans, know that dogs and cats are related? We know these things might be related because when we talk about them, we talk about them in the same way. So computationally, what we can do is we can look at their word co-occurrences. So in other words, right, so we can look at the other words that appear in these contexts. So you might say the word dogs sits somewhere near pet. Similarly, the word cat also sits somewhere near pet. And so sentences about dogs and cats are related via the word pets. You can, in effect, amplify the information within a very short document by looking at that word's similarity to other words in a broader context. So one way to quantitatively capture how near each other they are would be to calculate some kind of a distance between these co-occurring words. And we do have useful techniques for doing this. The most popular would be something like word2vec, which uses a neural net to embed these things into a vector space. And then you can use just algebra to calculate some distance. But something else that you might do is figure, okay, so how many sentences contain both of these words? If cats and dogs never show up in the same sentence, but they do both frequently co-occur with the word pets, right? How many hops does it take to get from cats to dogs? One hop is pretty close by, but if it's 100 hops away, maybe those things don't have anything to do with each other. So this is the intuition for our method. So we construct this graph structure, right, where the nodes are the words and the edges are occurrences of two words in the same context. And in the case of this system, we define the context as simply being in the same tweet. We have weights on the edges too, right? So the more that two words co-occur, then the heavier the edges. And in fact, the edges are basically lists of tweets that contain two words or nodes in the edge. So in this example, we have an edge between good and there because both those words appear in the same tweet. Similarly, we have an edge between bad and there because they were also in the same tweet. And let's say in some other tweet, in some other conversation that I haven't shown here, someone has said something about dogs and cats as pets. So we also have edges from dogs and cats to pets as well. As we establish more and more of these contexts, the edges become heavier, and the relationship between pets, dogs, and cats strengthens, possibly faster than the relationship between good and bad and there. And with more and more context, in fact, the word there branches out quite a bit more, and it hits a larger variety of co-occurring word nodes compared to pets. So another way to put this is that words that are low in information might be associated with a large variety of other words, so they branch out a lot, but words that are tightly related maybe don't branch out so much but have very heavy branches. Okay, so words that are commonly used in the same context are clustered together or form communities of nodes. If we generate this word connection graph, then we can look for these communities of nodes using a community detection algorithm and possibly tease out the topics. So the algorithm that we use is called Louvain, and it has a bit of historical use in previous Cortico and Lab for Social Machines research. So that influenced its choice, for this system. Louvain is in a class of algorithms that optimizes a thing called modularity. So what is modularity? So let's suppose we've got some algorithm like Louvain that takes a guess as to what the communities are. So the question we should ask is, okay, how can we quantify how good this labeling is? And modularity is a metric that encapsulates two different ideas. So the first idea is, okay, how many edges reside in the communities? So intuitively, we say community is a structure in which the nodes, it's very dense. There are a lot of interconnections between nodes. And two different communities don't have a lot of edges in common. They might have some, but not a whole lot. If they had a lot of edges in common, perhaps they should all be one community. So we can take this notion. We can say, all right, the fraction of the edges that sit inside of the communities should be as close to 1 as possible. This means most of the edges are in communities, and a very small amount of edges are between communities. OK, so that's principle number 1. Principle number 2 is how unique are these communities to this graph? So in the extreme case, where our community detection algorithm produces just a single all-encompassing community, so just like one label for everything, that wouldn't be very useful for us, right? So in other words, that community labeling isn't very unique to any particular graph, since it applies to all graphs. Right? It doesn't tell us anything special about this particular graph versus anything else if we just say, OK, everyone is in one group. So in my opinion, this last point is actually the hardest one of the two to think about. But consider this. OK, let's say that we have a graph with label communities. Then we go in and we mess with a bunch of edges. Let's say we randomly swap a ton of the edges. If the communities still make sense, then maybe those community labels weren't very interesting at all. Right? They just kind of generically apply to any kind of a network. So what we want here is we want symmetric. Right? We want a large number of edges to be included in the communities, but we also want a very unique set of labels, such that if you mess with the graph, then the labels no longer make sense. So more precisely, the modularity of a graph is defined to be the fraction of edges in communities minus the expected fraction of edges in those same communities in a randomly perturbed graph. The larger, the more the edges reside in the communities, and the stronger, more unique the labels are. Modularity optimization, then, is an algorithm that tries to optimize modularity. I hope that makes sense. So given some graph, right, we'd like to be able to assign the nodes into communities such that we get the largest modularity value we can. And calculating the optimal set of labels here is actually an NP-hard problem, so we use approximation algorithms for this. So how does Louvain work? Louvain is a greedy algorithm, and it consists of 2 steps that we repeat over and over again. So the first is that we initialize the state by putting every node in its own community. So you can see in the initial state, right, that's the graph in the lower left. Then for each node, we ask, OK, can we increase the modularity by reassigning this node to one of its neighboring communities? If so, we'll move it. Otherwise, we'll leave it alone. And then after this phase, so that's the top graph, right? You'll see that some of these nodes have been labeled. So the new communities here are coded in red, green, dark blue, and light blue. It's a little hard to tell. OK, so that's phase 1. So then for phase 2, what we do is we take this and we create a new graph by collapsing all of those communities into single nodes. So now we have a new graph, a new structure. And then we can repeat phase 1 on that. And we just keep doing this over and over again, just trying to increase the modularity with every new assignment. Once we can no longer increase the modularity, we're done. So applied to our word graphs, we get communities of words that show up in similar contexts often, and those tend to form topics or events. So some things that we had to deal with in practice. Louvain runs are determined by the size of the graph. So limiting the size actually goes a long way towards making things fast. So the first thing to note is that very densely connected words tend to be pretty low information. And these are words that have the largest number of edges coming out of them. So we do a pre-filtering step where we cut out the stop words. But the generally accepted list of stop words is pretty small. These densely connected words are not they're not stop words, right? So as an example, these are the words that come from a run of the algorithm over a day of tweets ranged through the Boston area. And we cut all of these words out. Now, there's an interesting question here. So what happens to a word like Elizabeth, which in this case appears because of tweets about Elizabeth Warren, who's a Massachusetts senator. So in a topic detection system, it might seem crazy to cut out the word Elizabeth, because surely, like, she must contribute some sort of weight somewhere in the math. But it turns out actually that in practice, if you cut her name out, or or a word like Trump, it actually doesn't seem to affect the quality of the clusters. And it's because the co-occurring language also has some kind of a significant pattern to it, the co-occurring words around her name or around Trump. So it's the case that the words people are using to describe some event involving Elizabeth Warren stick around, even though her name might actually get cut. And in a way, it's as if these communities are even more robust, because you can actually remove the centroid and still see the community there. Now, a really important thing to point out is that Louvain doesn't require you to specify a fixed k number of topics beforehand. So this is really, really key, because you would expect that the number of things of interest to not remain constant over time. So the second thing that we do after cutting out all these dense nodes is that we restrict the overall size of the graph. So I played around with different graph sizes, starting with large numbers and trying smaller and smaller ones. And at some point, the clusters become relatively stable. But the process was, it was just like me, like putting my finger in the air. Like, it wasn't really very rigorous at all. We also eliminate edges that have weight 1, i.e. 2 words that co-occur in exactly 1 tweet. And here are some examples of that. So these are pairs that are only showing up once per day. It's a bit less clear exactly how we interpret this. They seem to maybe have some information, but again, it doesn't seem to adversely affect the results. Okay, so here's the final algorithm. So we define word co-occurrence. So in this case, we're saying 2 words in the same tweet are co-occurring. We construct a graph where words are nodes and the edges are co-occurrence relationships. We filter out low information words by high frequency, low pairings. We pick the heaviest edges, and then we run community detection on it. So I've written this in a slightly abstract way, where you can swap out methods for number 1 and 5, but the general structure we haven't really changed. Okay, so that's enough theorizing. Is the proof in the pudding? So this is for a run over 1 day of Boston data. So here we have a list of the most connected words, i.e. the ones that our system drops from analysis. So this is the output for the first cluster. Here we're outputting the top 20 words in the cluster by frequency of use. The counts next to the word are the number of times that the word shows up in the entire collection of tweets. And you can see that the distribution of words, in this case, drops off about halfway through. And the tweet that's displayed is a representative tweet for the cluster. And I'll go into how we figured that one out later. This is the output for the second cluster, and this again is Elizabeth Warren related. This time is specifically about her opponent, Jeff Deal. This representative tweet, I think, actually fails to capture what the cluster here is about, I think, or either that or maybe the cluster is a little too mushy for us to actually have a good tweet. Traffic alerts always show up. As you might expect with an event detector that's drawing from local data. One really important thing to note about the system is a limitation I'll talk a little bit about later, is that the cluster definitions are mutually exclusive. So for instance, the word traffic can only show up in one cluster. So as a result, we don't tend to get more than one traffic topic unless there's a major incident like a car accident, in which case the word co-occurrence distribution around the car accident looks different than normal traffic conditions. Here we have an Ayanna Pressley tweet. Pressley had a surprise victory in Boston to become the Democratic nominee for the House, much like Alexandria Ocasio-Cortez did in New York. And the Pressley victory occurred 4 days before this data set. Anything of real local interest. Disabled cruise ship in Buzzards Bay. I think they survived. They have food on the ship, right? Okay, so it does turn out that we pick up a lot of stories of strong national interest, though that particular data set I showed is still slanted towards Boston talk. One of the reasons here is that the initial run here we count retweets. And the system tends to pick up language around the most popular tweets, though not always. And if we discount retweets, then we pick up much more local stories. Without retweets, the first couple of clusters are the same. They're about traffic in Elizabeth Warren. The next few clusters are a bit different, and they appear to be more hyperlocal. So in particular, too, the word co-occurrence distributions seem to be a bit more evenly spread out, which is what you might expect without the retweet amplification. So here's one example about Hurricane Florence, which was making its way up the coast at the time. And another thing of local interest, a very close race between Dan Koh and Lori Trahan. So just to be clear, up until now, I've only described the methodology for coming up with the word clusters. So really what we've got is this. So how do we go from the cluster definition on the left to a thing that a human can read on the right? And remember that the downstream application here is an overview page that a user should be able to quickly scan and then launch into other modes of discovery. We could just leave it at the keywords. But it turns out that there's actually substantial literature on what are called summarization techniques. And summarization involves generating some human-readable form of the word clusters. And the truly ambitious try to generate grammatically correct new sentences that describe the cluster. But we opted, instead, we're picking out just the best tweet that we can summarize. So summarization is an open and active area of research for members in the lab, but unfortunately there isn't a single accepted way for people to do it. And so we went with something that's quick and dirty instead. It's crude, but I would say the results are 60% of the time are decent. OK, so what we do is for each cluster, we look for the tweet that is closest by some measure of the collection of the words. And the rub then is to define what it means for a tweet to be close to a cluster. And for this, we turn to cosine similarity, which is a pretty standard technique. Cosine similarity says something like this. So imagine that you've got 2 points in space, and you want to know how close to each other they are. One way to tell is to draw 2 lines, one from the center of space to the first point, and then one from the center of space to the second point. And then you look at the angle between those two. If the angle is 0, right, which means that the cosine is 1, then you say that those 2 points are similar. And if the angle is 90 or cosine of 0, then they're perpendicular to each other, then they're very different. So though all of this is happening in a very high-dimensional space, we can better illustrate this just in 2 dimensions. So a particular cluster might be defined by the words co, trahan, and recount, which sits somewhere in space. And then some other tweet also sits in space, and its location is defined by the words in the tweet body. And the similarity measure between the two is the angle in green between those 2 points. So the closer the angle to 0, the more similar those 2 points are. What we do then is we take the word clusters and we put them into in this space where each of the words is 1 dimension, and then we take all of the tweets and we calculate the cosine similarity against each cluster. And a cluster's representative tweet is the one that has the highest cosine similarity. So it's brute force, but it works well enough to give our users a sense of what the cluster is about. A neat kind of a side effect of having these definitions of the clusters then is that after we discover some cluster, we can then apply it going backwards in time, which we've kind of done in research, but we haven't actually put into the product quite yet. So we can ask the question, OK, when did this event actually start to gain steam? And we do that using cosine similarity. One of the difficulties in creating an algorithm like this is that it's really unclear how we're supposed to evaluate the quality of the results. Like, we don't even know how to precisely define an event. Right? Are 2 different traffic slowdowns different events, or is slow traffic in general, is that just 1 event? When Presley won, we had a case where the algorithm started finding multiple viewpoints on the same event. This is a good thing if you're looking for multiple takes on Presley's win, or it's a bad thing if you think of it all as one thing. So it's unclear exactly how to resolve this in a way that fits all use cases. One thing that's really important to note, though, is that with the graph size reduction techniques, Louvain runs really fast. So calculating these clusters on a day's worth of tweets for a single city takes 2 to 3 seconds on a single core. Louvain speed was one of the primary motivations here for going down this route. At 2 to 3 seconds for calculating the events, we can actually have the user interactively tell us at what granularity they want the clusters. And so this is the thing that we're going to build into our product in the future. The speed of Louvain is a huge plus, but also the fact that we don't have to set a fixed k number of topics, right? Like in all the other techniques, you have to have some notion beforehand of how many things you're trying to discover. So this is this relieves us of that pressure. And by using words as nodes in the graph, we get to generate interpretable topics in the same way that LDA does. Okay, so what's next? So I've mentioned a few times now that the cluster definitions consist of words that are mutually exclusive. This seems to not be an issue in practice, though, like I said, evaluation is hard. So one thing that we'll be looking into is using a community detection algorithm that can generate overlapping communities. Conductance. So the standard right now is to optimize modularity. But modularity suffers from a tendency to ignore very small clusters. There are other measures that might be better if we really want to be able to focus on local stories, which maybe have smaller, smaller size clusters. So conductance is one way. And then the third thing is that we're going to work on a better evaluation technique so that we can tune the hyperparameters a bit more. Louvain. The version of Louvain that we're using has one resolution parameter, which I didn't talk about. So there's one thing to tune there. And we had this notion that we'd want to be able to minimize the number of clusters that maximizes the amount of diversity in the clusters. So in other projects in the lab, we'd previously used information theoretic methods to do this, so we might go with that strategy again. So you can think of diversity in a cluster similar to diversity in an ecology. So what's the variety of species in some ecosystem compared to the size of their populations? So there are quantitative ways for doing this, such as Simpson's index and Shannon entropy. Reducing word noise is a goal too. There are lots of words that don't produce extra information, but are not simply stop words. So here we've discovered some existing work on using co-occurrence word distributions to eliminate low information words. The rough intuition here is that you can take a distribution of words from a really big set, let's say an entire month worth of tweets, and then the distribution from a day worth of tweets, and you subtract out the month distribution, and you get like the unusual words for that day. We use a technique like this in a different part of the product, but it's definitely worth trying to import that over here. We're still working on tuning the algorithm for talk radio. So our ability to segment sentences through our speech recognizer isn't great. And also, spoken word is much more fluid and less perfunctory than tweets. So as a result, the words in the graph tend to have higher branching factors and produce larger and less meaningful clusters. One of the things that comes out of our talk radio clustering pretty consistently is a cluster of Liberty Mutual ads, because I guess they advertise on talk radio a lot. Anyways, yeah. So I'm optimistic that we'll figure this one out. So another network approach suggested by some researchers is to set up bipartite graphs. So this is a neat idea. So the basic idea is that you have a graph where you have a bunch of tweets on the left and then a bunch of words that they use on the right with the edges between them, and then you look for collections of words that form communities of tweets. The analogy is this: like, suppose you were to have a bunch of Twitter accounts on the left and then a bunch of famous Twitter accounts on the right. You can pick out who the movie stars are from the famous accounts because people on the left tend to follow them in droves, even if the movie stars themselves don't follow each other. And there are network methods for figuring out these bipartite matches. And then finally, as I mentioned before, we'll be looking at moving the hyperparameters directly into the user interface. If we can keep the algorithm fast, then we can give more tunable control to the user and perhaps bypass some of these evaluation problems. Okay, so lastly, I want to leave you with a reckless idea. Something that's been percolating in my mind, but is completely unsubstantiated and probably wrong. We've gotten a lot of press recently due to Word2Vec on using algebraic ways to do a lot of this language analysis, right? So we use these big clusters to train neural nets to put the words into a vector space. Or in the case of LDA, we think about the words as these topics as bags with statistical properties. The network analysis approach seems more right to me for some reason, because of the physical world, which must tie into how we learn language, and our brains are networks, and we live in social networks. They're better modeled as mathematical networks rather than vector spaces. So, like in the allegory of the cave, like I think of vector spaces and statistics as like the shadows on the wall projecting some distorted but still useful form of reality. But that networks are closer form to the essence of the thing. Yeah, so that's all I got. There's a link here to some academic reference material, the 3 papers that inspired this work. If you have any questions about the talk or Cortico, you can feel free to either grab me in chat. We're hiring, so if you want to do this kind of interesting computational work for social causes, come find me, especially if you're not a data scientist. I have an endless supply of batty researchers at my disposal, so I need the non-batty non-researchers. You can find me on Twitter spouting about this stuff, and I don't have a SoundCloud, but I do have a tiny letter. So, all right, thanks.